Hyperstruct's advanced learning and reasoning engine can turn past experiences into better future outcomes. We'll start with a realistic postmortem from an incident that took down production. Hyperstruct will extract key learnings from the postmortem, which then we'll use later in the future. The key thing to watch for is whether the prior incident changes the next implementation. We'll first run the Hyperstruct reasoning skill in Cursor to extract learnings from the postmortem. You could also use Cloud Code or any other agentic framework you wish. The skill will find the appropriate agent on the Hyperstruct registrar and use it to analyze the postmortem. I've asked the agent to use the Hyper Reasoning skill to analyze the following postmortem. So in this case, an engineer manually cleaned up MongoDB documents to reduce storage costs. Sounds like a good endeavor. And if we analyze the timeline, what happened was that when it went down, they went on to support. And support said, no, you got to delete less than 1,000 documents or 150 megabytes at a time. So that's a key learning. But let's see what else was down there. So we're going to let this run and let it extract the learning, and we'll see what happens in the next bit. A thing to note is that Hyperstruct is more than just an LLM wrapper. We have advanced natural language processing that does structured passes over the key evidence. We do conflict analysis and resolution. There's multiple deduplication algorithms. There's time decay on the memory, and there's much, much more. So we want to cut through all the noise and pull out what's really valuable. This is all wrapped in an easy-to-use API. Okay, cool. So the run finished, and what it found was that it used the Software Development Lifecycle Postmortem Learning Extractor. That's good. That's an agent that we prepared beforehand on the platform. It found a bunch of different learnings. It applied a confidence score, where the source was from, and that it set the privacy mode to be shareable, so there's nothing sensitive in there. That's a key part of the learning as well. And what we'll do now is move on to the next bit where we try to use these learnings in a related feature development. All right, so after storing the learnings, what we're going to do is build a new feature where we're going to implement a bulk deletion feature. On the left-hand side, we've got the baseline implementation where we ask it to build the bulk deletion feature, use type hints, deletes by folder, and it puts the outputs into run one bulk deletion and design notes. There's some assumptions as well. On the right-hand side, it's almost the exact same thing. The only difference is we're going to apply Hyperstruck Learning, and it's going to be using the learnings as part of the design constraints. Everything else should be pretty much identical. There's this last bullet point down here to list what learnings it used from for this feature as part of the design. So we're going to run both and see what we get. Okay, so now that it's done, let's analyze the runs of our two. So in run one is the baseline, and run two folder is the one that uses Hyperstruct Learning. Take a look at one, the implementation details. It's got some types. It's got an example protocol, some response types, and a fake implementation. So in this implementation, it has delete many and it has delete one, and all it looks like it's doing is that it's doing a loop, and then it'll delete each item and increment the count of the number deleted. So delete by folder also checks the folder ID, and it does a try delete many and try delete one depending on how many we provided. Okay, if it's an ID, then we delete that one. Okay, and then there's the main call as an example. We're going to quickly gloss over the design notes because we know that it didn't really learn anything. That's expected. Some simple acceptance criteria, delete by folder and whatnot. Some test cases and known risks. That's fine, it's following the instructions. Now let's start with the Hyperstruct Learning implementation. So we can already see that it's almost double the amount implemented. Let's start with the design notes because we asked it to list all its learnings. Okay, so we scroll down here, there's a stable ID for the learnings. And it found based on the postmortem, yep, keep deletes below 1,000 documents. That's what we expect to see, and 150 megabytes. Add some safety gates, and do not treat cleanup delete flows as just a low risk because they're not user facing. Threshold checks. Audit metadata is important as well. Okay, cool. So that looks pretty good. Let's see how it actually influenced this. I actually want to see if it also. Okay, so an important thing to note is that if the learning was used in the implementation, it'll reinforce the learning. So that way it surfaces next time, and that decay doesn't make it forget the learning if it's like not important. Okay, so right off the bat, I can already see that in the bulk deletion run 2, we've got max sync documents 1,000, max sync bytes 150 bytes, kilobytes, megabytes. Okay, so megabytes, 150 megabytes. And then we can probably find the implementation where it checks thresholds and stuff. Okay, max thresholds, max bytes. Yeah, that makes sense. Delete folder and files. It's gonna go delete many folder by ID. Okay, so already what we found from the postmortem, which would have been buried a long time ago, and it had a junior developer or somebody coming in without that context try to bulk delete, it would have brought production down again. In this case, it was completely prevented because we pulled learnings from the past. If you're interested, please reach out at hyperstruck.com and let me know what you think.